Hey, this is Ken from Coffee Crafters, and Bryce and I wanted to do a video on designing roast chambers for fluid bed roasters because, and some people might want to know, why the heck would I do that and share information with other roaster builders? And the short answer is because I learned so much from you guys from following you, and probably nobody has made more mistakes than I have in designing the roast chambers, so I've learned a lot over time, and I wanted to share you some new stuff that we have. So anyway, I'd like to start out talking about conical hoppers because conical hoppers are something that a lot of people will use, the DIY guys, and they work great. They have a performance window that we found out, and one of the things we did in the early days is I set out to develop a 5-pound roaster, which we did, the Artisan 5, our very first roaster that we did. And what I didn't do was a lot of testing on pressure and airflow to understand what could make it even more efficient. And so one of the things we did in the beginning, this was our original chimney that we did on our 5-pound roaster, 2 3/8 inch ID in the loft air tube going up through the old hopper that we had. And what I didn't realize at the time is if I actually made that chimney smaller and raised the air pressure inside the heat chamber, that I could loft larger loads at a lower CFM. And that's what we did. So when we did the XE hopper, it's 1 7/8 inch opening size on the tube. So if you look at the difference between these two, you'll see the difference there. And made a big difference in the amount that it lofted, whatever. Limitations on conical hoppers are in load size, because one of the things that happens with conical hoppers is as you increase the diameter of the opening size of the hoppers, like we bought a pallet of 12-inch hoppers thinking we were going to make higher capacity ones, and we just actually threw them all in the recycle bin and recycled them not long ago. What happens is, on the beam bed, as the width of the beam bed increases, the loft air that's going up through a conical hopper, that air spreads through the diameter of that beam mass, and it takes more and more air pressure to loft the beams. And here's a good example. This is about a 9-inch ID. We took the 12-inch ID and built the exact same hopper, put it on the old, I think it was on Artisan 6. And the Artisan 6 would loft about 15 pounds of coffee. As we increased the diameter of this to 12 inches, it wouldn't loft 12 pounds. And the reason is that it was dissipating the pressure of the loft air out through the top of the beam mass. And so I said, that's interesting. So I started taking, we're at the factory, and I was taking the roll former and forming cones in the center, and I kept putting diameter cones smaller and smaller and smaller, and as it got smaller, the volume that I could loft got bigger, the CFM got lower, and so that's where we kind of gathered that information up on conical hoppers. So that's one of the reasons why you run out of capacity. 10 to 12 pounds is something, and I'm talking about being efficient. I'm not talking about throwing massive amounts of heat at it. If you want to be efficient, it's really hard to get beyond 12 pounds. You give up something, and the reason is you have to use a lot more air, CFM, to establish the loft. And the pressure wave in a narrow hopper, like people who have a 3E and an XE, like they comment on this quite often, is that the 3E loft is a lot easier to control. So it's much less sensitive than it is in the XE. And the reason is, as the diameter of the hopper shrinks, the pressure wave, so that amount of pressure that it takes to establish, gets shorter and shorter and shorter, and so you feel like you have more and more and more control. We found that out when we were working on hoppers for the big roaster that we'll talk about here shortly. So that's the other thing that happens is you get a larger diameter conical hopper, the pressure wave gets wider and wider. And think about blowing high pressure air through a straw up through some kind of a seed mass, and then blowing it through a giant balloon and having to go through the other side. It builds up all that pressure and then it goes through. It's why in the beginning we didn't understand what was going on. We didn't understand the pressure wave issue in the Artisan 5 and 6, and so we had that little air fin in the bottom that had it broke up the airflow into 6 little vortexes, and it did away with that bubbling, the burping that happened. So anyway, so that's the thing with conical hoppers. There's somebody shared a website that had borosilicate glass. So if you're doing anything like 5 pounds or less, you could stick with like a 6-inch, 6 or 7-inch, borosilicate roast chamber. That would be kind of cool. It's kind of cool to look at it. People love those because you can see the beans roasting until they have to clean them and maintain them. Then they're not quite so much. But and if any of you want to use conical hoppers, there's a company in Toledo, Ohio, Toledo Metal Spinning. Go on ToledoMetalSpinning.com and you'll see the hoppers that we use. They have these. They come uncut because they're spun, so they're a big flat piece of metal that spins into a round. So you have to cut the bottom on them. And this is a standard size that they have. These are used for pharmaceutical, whatever. Here's another standard size. We've used this one in the XE through the Artisan 5 from the very beginning. So you have to cut the bottom off, put a pipe on, do whatever you're going to do. And that's a great source. And if anybody's interested, I can give them a link to the website. And it actually came from the Fluid Bed Roaster Forum. Somebody posted something on there some years ago, I think, on the borosilicate place where you get the glass. So bottom line with these is don't make the opening size too big. As you make the opening size too big going in, then you have to use more CFM, which overruns your heat element, whatever your heat source is. I see a lot of people building roasters out there, and I can tell by looking at it, now that I've learned what makes them efficient, they're gonna have to throw lots of heat at some of them because they're gonna be inefficient. So we learned all this stuff about conical hoppers. We thought, okay, we're the experts now. So when we went to start building horizontal air curtain hoppers, which are different, we transferred some of the math, those calculations that we had over to that, and found out that it had absolutely nothing to do with developing a horizontal air curtain hopper. And so we're working on the big roaster, the Valenta 25 now, and the original hopper on the Valenta 25 was not performing well. I mean, it was really inefficient. We got the loft going, so we're trying to, because I used to say loft, larger loads at a lower CFM. I carried that language into these, had nothing to do with what made that efficient. And so the first one, it lofted fine, but the problem is it just took too long to roast, and we couldn't figure out, we've got lots of BTUs going at it, it should be doing better. And it wasn't until we started simulating airflow in SolidWorks that we stopped building prototypes and started building more and more prototypes in the computer before we went out. And this was really exciting for us because Bryce is going to insert a little video here of a computer simulation of a hopper that does not work. So if you look at the simulation and you see the air start to go up, the orange air is the fastest and it goes down through yellow and green, and the blue air is the air that's moving the slowest. So, and you can see on the simulation that the airflow, the hot airflow coming out that was lofting the beans, went through, contacted the beans, and then immediately evacuated the roast chamber. So the roast air that we were spending all the electricity to heat up, it was just exiting the machine. So I actually met a thermodynamics engineer one evening. We were talking about what we're doing, and he designs furnaces for mining, for smelting ore and stuff. And he was talking, and he goes, well, show me a picture of it. I actually had a picture on my phone of the roast chamber, and he goes, no, that won't work. And he explained to me about creating a vortex inside of the roast chamber for horizontal air curtain. You can tell when you look at like the Newhouse Neotech roaster, they got a really good simulation of their beans. They've used the same software when they did theirs, because I can tell by their design that they're keeping that air engaged in the beam mass. So now you look at another simulation of, our second simulation is a simulation that we worked on for a long time until we got it just how we wanted it. And you can see in this simulation, the air going up through the beam mass in the bottom and then creating a vortex inside. And what we did with this design was the curvature part at the top and the opening size going out were two of the critical factors. So we moved those around. We could actually move in the simulation by changing the angle. We could center that vortex of air spinning around in the section of the roast chamber that we wanted. And so what happens in this one, which turned out to be hugely efficient, was the air goes up and contacts the beam mass the first time. And that's when it lofts the beams and they're doing their thing. Then the hot air goes up and around the top and re-engages the beam mass on the way down. You can see in the simulation all that dark blue air going out the top. That's low pressure air moving at a low velocity, and it's even. So when you turn it on and you're lofting the beams, you can put your hand across the top of that, and it's real even airflow out the other side. And so if you're going to build one with a horizontal air curtain, that rounded part at the top means a lot. Now we choked down the chimney, so Bryce, go back here. Here's a picture of a roast chamber that we designed. So one of the things that we did when we were doing the simulation is we started choking this off, thinking that if we ran this around farther, that it would make that vortex even stronger, which did exactly the opposite. What happened when we decreased this opening size, and we were down to about 2.5 inches, I think, it raised the air pressure inside of the roast chamber, and this air came around like this. High pressure air blew the hot air right out here. So we backed off until, and then we watched the simulation, the colors in the simulation, until we moved that vortex air mass inside of the roast chamber, inside of a full load. So we've been torturing this one, and when you're roasting a pound, it's not very full. So what you can see is the chaff that comes off gets stuck in that vortex and goes around and around and around, and then it finally loses enough of its weight, it'll go out. But you can see the vortex working in there on the chaff. Another thing that we learned is if you're doing a horizontal air curtain, and Bryce, you want to come in here and look at that screen on the bottom. So you can't use, like on one of these hoppers, you can see the perforated screen on the bottom. We just have a perf pattern. I think this is a 70 or 75% open. Horizontal air curtain, you want to use elongated slots, and the issue is, especially if you're blowing it up at an angle, because when you want to dump, if you just want to open a door and it comes out at 22 degrees or more, as you have to dump those, the air goes straight up through here. If you got all those perfs in there, it shoots the air to the sides through them. Each one's are only little cylinder that the air has to pass by, and that makes it more efficient. So anyway, those are some of the things that we learned in designing horizontal air curtains. When I was doing some training with Michael Sivitz, way back when, he's the one who explained to me too about, because he understood the limitations of a conical hopper. So when you get past 10 pounds, 12 pounds, if you remember Michael's, some of his machines, he had a 12 pound in a conical hopper. He stopped at that. The reason he went from that to the horizontal air curtain was because of efficiency. I can tell by doing simulations now some of the performance problems that he had in his quarterback machine, because he throws a massive amount of heat at that. They're using natural gas, so they just turn the heat up. And his vortex is probably not quite tuned in, but still it was a great machine. There's tons of them still out there running. So anyway, so that made an issue with that. Anyway, if any of you are building a roaster and you have some questions, you want some more information, I help the DIY guys all the time. It's kind of one of my hobbies. So if you want to just email me, ken@coffeecrafters.com, I would be happy to talk to you about your design and share with you some of the mistakes I've made. So hopefully it can save you a little bit of heartache doing some of the things. I know there was a discussion here recently about the type of materials that used in them. That was really interesting because actually cold rolled steel does have a better heat transfer. It doesn't apply to us because we NSF our machines, and that only stainless steel with a certificate that we get from the steel manufacturer would be accepted for our food safety rules. But for the DIY guys, absolutely, you can use whatever it is that you can use. One of the things on the material, heat chambers are different. We use cold rolled steel for the heat chambers in the early days until we saw them run for 3 or 4 or 5 years, and they started spalding inside and flaking off. And so we went back to stainless steel in the heat chamber just so they last for a long time without spalding. Anyway, that's it. I'm gonna go back to work, build some more roasters. But if you DIY guys want to BS about building roasters, I'd be more than happy to talk with you. And we'll see you later.